February 18, 98. Manhattan construction site. European engineering reports would never capture what American steelworkers discovered that morning. Hot-driven rivets glowing cherry red, hammered into 1890 rolled steel beams using methods European experts called obsolete. Through construction steam and hammering noise, American crews built frames where rolled steel beams would never crack at joints, while modern welded steel would fail within decades. No advanced welding equipment, no seamless connections, no heat-affected metallurgy. Yet these primitive riveting methods created joints more durable than anything modern engineering promised. European specialists insisted welded connections represented the future, stronger, faster, more scientific than crude hammering. American building owners demanded welded joints to slash construction costs and time. The engineering establishment declared riveted steel obsolete, inefficient craftsmanship from America's industrial past. But in the heart of Manhattan, workers were proving something no textbook predicted. The old rolled steel beams wouldn't just survive. They would outlast every welded innovation that followed. The winter of 1897 brought more than snow to the construction sites scattered across Manhattan's rising skyline. Steel mills in Pittsburgh were rolling beams longer and heavier than ever before, and the race to build America's first true skyscrapers had begun in earnest. Frank Harrison stood on the muddy construction lot at the corner of 23rd and Broadway, watching steam rise from the morning coffee of workers who would soon be climbing steel frames 20 stories into the sky. The age of masonry-bearing walls was ending, and Harrison knew it. No amount of brick and mortar could economically support the loads these new buildings demanded. Harrison pulled his notebook from his wool coat and flipped to the calculations he had been refining for months. A typical 20-story steel frame would require girders carrying loads of 400 to 600,000 pounds each. Beams spanning 30 to 40 feet between columns would weigh 2.5 tons apiece. The mathematics were unforgiving. Traditional European construction methods, with their thick masonry walls and conservative spans, simply could not accommodate the heights American commerce demanded. But the solution everyone seemed to embrace made Harrison uneasy. The established engineering firms in New York, particularly those led by European-trained architects, had already declared welding the future of steel construction. They spoke with authority about seamless connections, reduced labor costs, and faster erection schedules. Edward Whitman, the senior welding engineer at Morrison & Associates, had been making his rounds to potential clients all winter, carrying metallurgical studies and cost projections that promised welded joints would revolutionize the industry. Harrison had sat through more than one presentation where Whitman dismissed riveted connections as crude, labor-intensive relics of America's industrial adolescence. But Harrison had spent his apprenticeship years in the steel mills of Ohio, watching rolled beams emerge from furnaces, learning how metal behaved under stress, expansion, and time. He understood something the welding advocates seemed to overlook. Buildings moved. Wind loads pushed and pulled at tall frames. Thermal expansion and contraction occurred daily as temperatures changed. Dynamic loads from occupants, machinery, and weather created subtle but constant motion in every structural joint. Rigid welded connections, for all their apparent strength, concentrated these stresses at single points. Hot-driven rivets, properly installed, distributed loads across multiple fasteners and allowed the micro-movements that prevented fatigue cracking. The challenge Harrison faced was not simply technical but logistical and economic. Installing riveted connections meant heating each rivet to cherry red temperature, approximately 1900 degrees Fahrenheit, then driving it through precisely aligned holes in multiple steel plates before the metal cooled. A typical beam-to-column connection required 12 to 20 rivets, each one demanding perfect timing and craftsmanship. Harrison calculated that a 20-story building would need more than 200,000 rivets, each one heated, placed, and hammered by skilled crews working high above the city streets. The scope of the undertaking became clearer each day as Harrison walked the steel mills and fabrication yards. Rivet bars had to be hot-rolled to exact specifications. Holes in beams, columns, and connection plates had to align within tolerances of 1/16 inch. Field crews had to maintain portable forges, heat rivets to the proper temperature, and drive them before the steel cooled and hardened. The welding alternative promised to eliminate much of this complexity. Welders claimed they could join steel plates on site with continuous seams, faster installation, and fewer skilled workers required. Building owners were listening. William Riley, the developer who had commissioned Harrison's latest project, a midtown Manhattan office block, made his priorities clear during their December meeting. Construction costs were rising, skilled workers were scarce, and every week of delay meant lost rental income. Riley had heard Whitman's pitch about welded connections and wanted to know why he should pay premium rates for what appeared to be obsolete methodology. Harrison had won the argument, but barely. He convinced Riley that riveted connections offered proven durability, better fatigue resistance, and the ability to accommodate the subtle movements that tall buildings experienced. But the contract came with conditions. The steel frame had to rise at a rate of 3 to 4 floors per month. Any significant delays would trigger a review of the construction method, with welding as the alternative. Harrison signed the agreement knowing he was betting his reputation on the skills of rivet crews and the reliability of methods that much of the engineering establishment now considered outdated. By February of 1898, the first steel shipments began arriving at the construction site. Harrison watched workers unload beams that stretched 40 feet and weighed nearly 3 tons each. The building's frame would ultimately contain approximately 3,000 tons of rolled steel. Columns built from multiple plates and angles would support roof and floor loads exceeding 200,000 pounds each. The cumulative number of rivet holes that had to be drilled, aligned, and filled numbered in the tens of thousands. As Harrison stood watching the first steel columns being positioned by steam-powered derricks, the full weight of his decision settled over him like the smoke from the nearby forging furnaces. Miguel Santos, the Portuguese foreman who would lead the rivet crews, approached with a bundle of steel bars that would become rivets. Santos had spent 15 years perfecting the craft of hot-driving rivets, timing each blow of the hammer, listening for the sound that indicated proper head formation, feeling through the tools when the metal had achieved the right temperature and deformation. The schedule board mounted near the construction shanty showed the progression Harrison had promised. Floor 1 by March 15th, Floor 5 by May 1st, Floor 10 by July, and the completed frame topped out by November. One misdriven rivet that failed inspection could delay installation. One alignment problem could require removal and redrilling of connection plates. One slip in the coordination between heating, placing, and driving could compromise the clamping force that held the entire system together. Harrison pulled his coat tighter against the February wind and watched the first bundle of rolled steel beams being hoisted into position. The forging furnace blazed nearby, ready to heat the first rivets to cherry red temperature. In workshops and engineering offices across the city, advocates of welded construction were already predicting his failure. Only American ingenuity and the skilled hands of workers like Santos stood between Harrison's vision of enduring riveted frames and the conventional wisdom that declared such methods obsolete. The promise of a building that would stand for generations hung in the balance, suspended between tradition and innovation, craft and efficiency, in the space where glowing steel met the hammer's blow. The first steel column rose on March 3, 1898, its built-up I section silhouetted against the gray Manhattan sky. Harrison watched the derrick operators position the 14-inch by 14-inch column, its flanges fabricated from 1-inch thick plates designed to carry 200,000 pounds of building load from roof to foundation. Miguel Santos and his rivet crew stood ready beside their portable forge, the coal fire already glowing white-hot in preparation for the connections that would join this column to the girders arriving on the next railway car. Santos pulled a rivet from the forge with his tongs, the steel bar glowing cherry red at 1900 degrees Fahrenheit. The rivet measured 3/4 of an inch in diameter, its length calculated to penetrate through the column flange, the girder connection plate, and still provide enough material to form a second head under the hammer. He dropped the hot rivet through the pre-drilled hole and positioned his pneumatic hammer while his partner held the bucking bar against the original head. The compressed air hissed, the hammer struck, and gradually the rivet tail began to mushroom into a perfect second head. As the metal cooled and contracted, it pulled the steel plates together with a clamping force Harrison estimated at 15,000 pounds. But Santos did not stop with one rivet. Following Harrison's specifications, each beam-to-column connection would receive 16 hot-driven rivets arranged in a distributed pattern across the connection plates. This was Harrison's breakthrough insight, developed through years of studying how loads moved through steel frames. Rather than relying on a few large fasteners or a single welded seam, the 16 rivet pattern spread the connection loads across multiple points. When wind pushed against the building, when thermal expansion moved the steel, when dynamic loads from occupants created vibrations, no single rivet carried the full stress. The load shared among 16 fasteners, each contributing its 15,000-pound clamping force to maintain the integrity of the joint. Clara Beaumont arrived at the site as the third column was being positioned, her materials testing equipment packed in a leather satchel that had become familiar to construction crews across the city. She set up her instruments to measure the clamping effectiveness of Santos's work, checking rivet head formation and plate contact. Her measurements confirmed what Harrison had calculated. The distributed rivet pattern created connections that could accommodate the micro-movements inherent in tall building frames without concentrating stress at rigid points. The rivets allowed subtle deformation while maintaining structural continuity, a mechanical behavior that welded joints, with their heat-affected zones and rigid continuity, could not replicate. By the end of March, the frame had reached the fourth floor, steel girders spanning 30 to 40 feet between the columns, each girder weighing 2,500 pounds and requiring precise placement by the steam-powered derricks. Santos had organized his crew into an efficient rhythm. While one gang heated rivets in the forge, another positioned connection plates, and a third drove the hot rivets before they cooled beyond workable temperature. The crew was achieving 120 rivets per hour, a rate that kept pace with the steel erection schedule Harrison had promised. The building owner, William Riley, visited the site in early April to inspect the progress. He found Harrison standing beside a connection where 32 rivets joined a major girder to two columns, the joint designed to carry loads exceeding 400,000 pounds. Riley ran his hand along the smooth rivet heads, feeling the tight contact between the steel plates. The welding advocates had promised him faster installation and lower labor costs, but he could not argue with the evidence before him. The frame was rising at 4 floors per month, ahead of the schedule Harrison had committed to in their contract. Santos paused in his work as Riley examined the connections. Speaking in the careful English he had learned during 15 years of American construction work, the Portuguese foreman explained his process. "We heat until the rivet glows like the sun, drop it through the hole while the metal is soft, then hammer until the tail starts to spread like a flower opening. If the plates don't pull tight together, the inspector makes us remove it and start again. Every rivet must grip with the full strength." Riley nodded, understanding that the craft Santos described could not be rushed or simplified without compromising the connection quality. Through the spring and summer months, the frame continued its steady ascent. By July, Harrison stood on the 10th floor, looking down at the organized chaos of 300 workers coordinating the placement of steel that now totaled 1,500 tons. 60 carpenters worked on concrete forms for the floor slabs. 30 rivet crews maintained the rhythm of heating, placing, and driving that had become the heartbeat of the construction site. 10 inspectors moved through the work, checking hole alignment within tolerances of 1/16 inch, verifying rivet head formation, ensuring that every connection met the specifications Harrison had developed. The moment of awe came in September, as the frame approached the 20th floor. Harrison watched a derrick lift a girder assembly weighing 4 tons, its length stretching 40 feet, slowly positioning it atop the growing steel skeleton. The girder would be secured with 18 rivets at each end, 36 fasteners distributing the massive loads through connections that had to resist not only the static weight, but also the dynamic forces of wind, thermal movement, and occupancy loads that would act on the structure for decades to come. But the precision required for such connections created inevitable challenges. On a humid morning in August, As crews attempted to position a girder at the 15th floor, the connection plates refused to align. The holes that had been drilled in the fabrication shop had shifted slightly due to thermal distortion during transport and handling. Santos examined the misalignment with his measuring tools and shook his head. The tolerance exceeded the 1/16 inch specification Harrison required for proper rivet installation. The solution required careful coordination. The rivet crew removed the girder using the derrick, carried it to a temporary work platform, and used portable drilling equipment to enlarge the holes to the proper alignment. The cost of the rework was minimal compared to the risk of installing rivets in oversized holes, which would compromise the clamping force and potentially create fatigue problems years later. Harrison supervised the corrective work personally, knowing that the long-term performance of riveted connections depended on maintaining installation standards even when schedule pressure mounted. By October, the steel frame towered 20 stories above Manhattan streets, its 2,900 tons of rolled steel held together by more than 200,000 rivets. Each rivet represented the skill of workers like Santos, the precision of Harrison's engineering specifications, and the commitment to craft over convenience that distinguished American construction methods from the efficiency-focused alternatives promoted by the welding establishment. The building stood as proof that distributed loads, multiple fasteners, and a combination of structural movement could create connections more durable than rigid joints that concentrated stress and resisted the natural behavior of steel under load. The blizzard struck Manhattan on February 14, 1899, just as Harrison believed his gamble on riveted construction had been vindicated. 18 floors of the steel frame stood completed, only 2 floors remaining before the scheduled March topping out ceremony that would mark his triumph over the welding advocates. The thermometer outside the construction shanty plunged to 10 degrees below zero, and the wind howled across the exposed steel structure with a ferocity that made the entire frame creak and groan like a ship in heavy seas. Miguel Santos climbed to the 15th floor at dawn, conducting his routine inspection of connections before the crews began work. The steel had contracted in the brutal cold, and every joint in the frame had shifted slightly as thermal stresses redistributed loads through the structure. Santos moved methodically from connection to connection, checking rivet heads for any signs of distress, when his experienced eye caught something that made him freeze. On the northwest corner connection, where a major girder joined the column, one rivet head showed a hairline crack running from its edge toward the center. Within an hour, Harrison stood beside Santos examining the failed rivet with a magnifying glass. The crack was unmistakable, a dark line that had opened in the cold steel as thermal contraction stressed the connection beyond its design limits. Harrison's heart sank as he realized what this discovery would mean. William Riley would arrive at the site within hours for his weekly progress inspection, and Edward Whitman had been making regular visits, waiting for exactly this kind of failure to vindicate his welding advocacy. Riley's reaction exceeded Harrison's worst fears. The building owner stared at the cracked rivet head, then turned to face Harrison with barely controlled fury. "This is exactly what Whitman warned me about. Riveted connections failing in the field, threatening the structural integrity of the entire building. I want welding crews on this site by tomorrow morning, and I want every remaining connection made with welded joints instead of these primitive rivets that crack under stress." But Harrison refused to accept the simple explanation that satisfied Riley's anger. He organized a detailed investigation of the failed connection, bringing Clara Beaumont to the site with her materials testing equipment and metallurgical analysis tools. Beaumont's examination revealed the true cause of the failure. The crack had not originated in the rivet itself, but in the steel plate adjacent to the rivet head. The plate material, typical of 1890s steel production with approximately 0.15% carbon content, had experienced low-temperature embrittlement that created a brittle fracture zone around the rivet. More significantly, Beaumont's analysis showed that Harrison's 16-rivet connection pattern had functioned exactly as designed. Despite one rivet showing stress cracking, the remaining 15 fasteners continued to carry the full connection load without distress. The distributed load pattern had prevented catastrophic failure of the joint, demonstrating the redundancy that made riveted connections superior to single-point welded joints under extreme conditions. The vindication came too late to prevent the crisis that engulfed the project. Riley ordered a complete work stoppage while every connection in the building underwent additional inspection. Santos and his crews stood idle for a week while Beaumont tested rivet samples, measuring ultimate tensile strength of 45,000 pounds per square inch and elongation of 20%, values that exceeded the specifications Harrison had established for the connections. The delay pushed the completion date back 2 weeks and added substantial cost overruns to the project budget. Edward Whitman seized the opportunity to press his case for welded construction. He arrived at the site with documentation from a rival building project in Chicago that had used welded connections throughout its steel frame. The Chicago building, completed 2 years earlier, had initially been celebrated as a demonstration of modern welding technology's superiority over old-fashioned riveting methods. But Whitman's documentation revealed a troubling development. The Chicago building had begun showing weld cracks after only 24 months of service, particularly in connections subjected to freeze-thaw cycles and dynamic loading conditions. Harrison brought in a consulting engineer from Philadelphia who specialized in comparative analysis of connection fatigue performance. The consultant presented data from multiple studies of riveted structures built in the 1880s and 90s, showing that properly installed riveted connections maintained their structural integrity even after decades of service. The consultant explained that riveted joints accommodated the micro-movements that occurred in steel frames without creating the stress concentrations that plagued rigidly welded connections. The welded connections in the Chicago building had failed because the welding process created heat-affected zones where the steel microstructure had been altered by the intense temperatures required for fusion. These zones exhibited different mechanical properties from the base metal, creating areas of hardness variation and potential brittle fracture. When the building experienced thermal cycling and dynamic loads, cracks initiated at the weld toes and propagated along the heat-affected zones, requiring expensive repairs and ongoing inspection programs. But the technical vindication could not erase the emotional impact of the setback on Harrison and his team. He stood on the cold steel decking of the 18th floor, watching his crews idle below, while Riley reviewed cost overrun projections and threatened to terminate the riveting contract. The schedule board in the construction shanty now showed a red-lettered notation, delayed 1 week, and investor confidence in the project had been shaken by reports of structural failures and work stoppages. Santos approached Harrison as the engineer stared out at the Manhattan skyline, the Portuguese foreman's weathered hands gripping his coat against the February wind. "Mr. Harrison, my crews know their work is good. Every rivet we drove was heated proper, hammered true, and cooled to full strength. One bad piece of steel plate does not make our method wrong." Santos paused, then continued with quiet conviction. "The building stands strong. The connections hold. We will finish this frame and it will outlast any welded building they can build." Harrison nodded, drawing strength from Santos's unwavering confidence in their craft. He revised his construction plan to address the concerns raised by the rivet crack incident. Additional inspection protocols would verify every connection after installation. The inspection intervals would be increased for connections exposed to severe weather conditions. Temporary stiffeners would be installed to provide additional support for critical connections until the building's heating system came online and moderated the thermal stresses that had caused the initial failure. The week of delays had tested not only the structural integrity of the riveted connections, but also the resolve of everyone committed to proving that American construction methods could deliver superior long-term performance. Harrison understood that the failure of a single rivet in extreme conditions had provided his critics with ammunition, but the behavior of the overall connection system had validated his fundamental design philosophy. Distributed loads, multiple fasteners, and accommodation of structural movement had prevented catastrophic failure and demonstrated the redundancy that would serve the building well throughout its service life. As work resumed on February 22nd, Harrison watched Santos's crews return to their rhythm of heating, placing, and driving rivets for the final 2 floors of the steel frame. The setback had been costly and demoralizing, but it had also provided proof that riveted connections could survive conditions that would have caused rigid welded joints to fail catastrophically. The true test of Harrison's innovation lay not in avoiding all problems, but in demonstrating that his distributed rivet patterns could accommodate the inevitable stresses and movements that would challenge the building throughout its lifetime. The resumption of work on March 1st marked a turning point in both technique and morale for Harrison's rivet crews. Miguel Santos had used the forced delay to refine his installation procedures, organizing his gangs to achieve even greater efficiency in the heating and driving process. The portable forge now operated at optimal temperature throughout the workday, maintaining the cherry red heat required for proper rivet installation without the temperature fluctuations that could compromise metal properties. Santos's crews were consistently achieving 120 rivets per hour per gang, a rate that exceeded Harrison's original projections and demonstrated the superiority of skilled craft over industrial shortcuts. The vindication Harrison needed arrived in the form of disturbing reports from Chicago. The rival building that Edward Whitman had cited as proof of welding superiority was experiencing widespread connection failures after less than 3 years of service. Clara Beaumont traveled to Chicago to investigate the failures personally, returning with photographic documentation and metallurgical samples that revealed the fundamental weakness of welded steel construction. Crack propagation along weld toes had become endemic throughout the building's frame, particularly in connections subjected to cyclic loading and thermal stress. Beaumont's analysis explained the mechanism behind the Chicago building's failures with scientific precision that Harrison used to educate Riley about the superiority of riveted connections. Welded joints created heat-affected zones where the intense temperatures required for fusion altered the steel's microstructure, creating areas of grain growth and hardness variation that became preferential sites for crack initiation. The welded connections acted as single rigid points that concentrated all connection stresses at the fusion line, preventing the micro-movements that allowed steel frames to accommodate thermal expansion, wind loads, and dynamic occupancy forces. Harrison's riveted connections operated on entirely different mechanical principles that proved superior under real-world loading conditions. The hot-driven rivets created clamping forces that pulled steel plates into intimate contact while maintaining discrete fastener points that distributed loads across multiple locations. When the building experienced thermal expansion during summer heat or contraction during winter cold, the riveted connections allowed subtle relative movement between plates without creating stress concentrations. The rivet shanks could deform slightly within their holes. The clamped plates could experience microslips at their interfaces, but the overall structural integrity remained intact because no single fastener carried the entire connection load. The Chicago building's welded connections had no such flexibility. The rigid fusion between steel plates created monolithic joints that resisted all movement, concentrating thermal stresses and dynamic loads at the weld metal boundaries. When these stresses exceeded the material's fatigue endurance limits, cracks initiated and propagated along the heat-affected zones with devastating consequences. The building owners faced expensive remedial programs involving crack repair, ongoing inspection requirements, and ultimately the replacement of numerous welded connections with mechanical fasteners that could accommodate structural movement. By the middle of March, Harrison's steel frame had reached the 19th floor, and the rhythm of construction had achieved a precision that impressed even skeptical observers. The derrick operators could position 40-foot girders weighing 4,000 pounds with accuracy measured in fractions of an inch. Santos's rivet crews had perfected the coordination between heating, placing, and driving that allowed them to complete 18 rivet beam-to-column connections in less than 2 hours. The inspection protocols that Clara Beaumont had established verified that hole alignment remained within 1/16 inch tolerances, and that rivet head formation met the specifications Harrison had developed for optimal clamping force. The culminating demonstration occurred on March 28th, as Harrison prepared to install the final girder assembly at the 20th floor. The massive steel beams stretched 40 feet in length and weighed 4 tons, representing the heaviest single component in the entire building frame. Harrison arranged for instrumentation to measure the load distribution through the connection as the girder was positioned and secured with 36 hot-driven rivets, 18 at each end of the span, The measurements confirmed that no individual rivet carried more than its proportional share of the total load, validating the distributed stress patterns that made riveted connections superior to single-point welded joints. William Riley witnessed the installation personally, standing on the steel decking as the derrick lifted the final girder into position. The building owner watched Santos's crews heat and drive the last rivets of the structural frame, each fastener representing the culmination of techniques that had been refined through months of demanding construction work. When the final rivet cooled and contracted, pulling its steel plates into permanent clamping contact, Riley acknowledged what the evidence had demonstrated. Riveted connections had delivered both the structural performance and construction schedule that Harrison had promised. The completed statistics told the story of Harrison's achievement with quantitative precision. The steel frame contained 2,900 tons of rolled structural steel, connected by 212,000 hot-driven rivets. The average beam-to-column connection used 18 rivets arranged in distributed patterns that shared loads among multiple fasteners. Each rivet maintained clamping force of approximately 15,000 pounds, creating connection capacities that exceeded the design loads by comfortable margins while accommodating the micro-movements that prevented fatigue crack initiation. Harrison stood on the roof of his completed building as the sun set over Manhattan on April 10, 1899. The steel frame around him swayed subtly in the evening breeze, not rigid like a welded structure that would concentrate stresses and eventually crack, but resilient like a living organism that adapted to the forces acting upon it. Every rivet in the building represented hours of skilled labor, precise temperature control, and careful installation procedures that could not be rushed or simplified without compromising long-term performance. The breakthrough that Harrison had achieved extended far beyond the successful completion of a single building project. He had demonstrated that American construction methods, based on skilled craft and mechanical understanding rather than theoretical efficiency, could deliver structural performance superior to the industrial shortcuts advocated by the welding establishment. The riveted connections in his building would continue to carry loads and accommodate movement for decades, while welded structures would require ongoing maintenance and eventual replacement of failed connections. Miguel Santos joined Harrison on the roof as the city lights began to twinkle below them. The Portuguese foreman carried his rivet hammer, the tool that had shaped thousands of connections throughout the building's steel frame. "Mr. Harrison, we proved that the old ways can be the best ways when they are done with skill and understanding. These rivets will hold long after we are gone, because we built them to work with the steel instead of fighting against it." Harrison nodded, understanding that Santos had articulated the fundamental principle that distinguished their achievement from the failures plaguing welded construction. The correct mechanism mattered more than apparent sophistication or theoretical efficiency. Hot-driven rivets properly installed in distributed patterns created connections that worked in harmony with the natural behavior of steel under load, thermal stress, and time. The triumph belonged not to advanced technology, but to the wisdom embedded in techniques refined through generations of American craftsmanship and engineering experience. The building opened to its first tenants in May of 1900, and Harrison maintained his office on the third floor for the next 5 years, monitoring the performance of every connection in the steel frame. The riveted joints behaved exactly as his calculations had predicted. No connection failures occurred during the building's first decade of service. No unexpected settlement developed in the foundations. No fatigue cracking appeared in the beam-to-column connections that carried the daily cycle of occupancy loads, thermal expansion, and wind stress that challenged every tall building in Manhattan. By 1910, Harrison's building had become a landmark of structural reliability in a city where newer construction increasingly relied on welded connections. The welding advocates had promised faster erection and lower costs, and the construction industry had gradually adopted their methods for steel frame buildings throughout the 1920s and 30s. But by 1940, disturbing reports began circulating among structural engineers about premature failures in welded building frames across the country. Harrison learned of these failures through his correspondence with Clara Beaumont, who had established herself as a leading authority on connection fatigue and structural inspection. Beaumont's investigations revealed a pattern of weld toe cracking that appeared in buildings less than 2 decades old. The rigid welded connections that had been celebrated for their structural continuity were proving vulnerable to the cyclic loading and thermal stress that riveted connections accommodated without distress. Buildings in Chicago, Detroit, and Pittsburgh were requiring expensive inspection programs to monitor crack propagation in welded joints, while the riveted structures from the 1890s continued to perform without maintenance. The mechanism of welded joint failure became clear through Beaumont's metallurgical analysis. The heat-affected zones created by welding had altered the steel microstructure in ways that created preferential sites for crack initiation. The rigid continuity of welded connections concentrated all thermal and dynamic stresses at single points, preventing the micro-movements that allowed riveted joints to distribute loads across multiple fasteners. When these concentrated stresses exceeded the fatigue endurance limits of the heat-affected steel, cracks initiated at weld toes and propagated along fusion lines with consequences that threatened the structural integrity of entire building frames. Harrison visited his building again in 1920, standing in the same 20th floor location where he had watched the final girder installation 21 years earlier. The steel frame around him remained as solid and stable as the day it was completed, showing no signs of the connection distress that plagued newer welded structures. A young construction supervisor named Robert Chen, working on a neighboring building project, approached Harrison with questions about the riveted frame that had become famous among New York contractors for its enduring performance. Chen represented a new generation of builders who had been trained to view welding as the natural evolution of steel construction technology, but his experience supervising repairs on welded buildings had created doubts about the superiority of rigid connections. "Mr. Harrison, we've been told that welding represented progress, that riveted connections were obsolete methods from the old days. But the welded buildings we've constructed in the past 15 years are showing problems that your riveted structures never developed. What did you understand about steel behavior that we missed?" Harrison walked Chen through the fundamental principles that had guided his connection design. Steel moved. Thermal expansion and contraction occurred daily as temperatures changed. Dynamic loads from wind, occupancy, and mechanical equipment created cyclic stresses that acted on every joint thousands of times each year. Rigid welded connections fought against these natural movements, concentrating stresses at single points until fatigue cracking became inevitable. Riveted connections worked with the steel's natural behavior, distributing loads across multiple fasteners and allowing the micro-movements that prevented stress concentrations. The broader impact of Harrison's innovation extended far beyond the performance of a single Manhattan office building. American builders had adopted riveted steel frame construction throughout the period from 1890 to 1930, creating iconic structures like the Flatiron Building, completed in 1902 with a steel skeleton held together by thousands of hot-driven rivets. These buildings established American construction methods as the global standard for steel frame durability and performance, demonstrating that skillful craft could deliver structural longevity superior to industrial shortcuts. The quantitative comparison between Harrison's building and modern welded construction told the story with mathematical precision. His 1900 building contained 212,000 rivets connecting 2,900 tons of steel. Each connection distributed loads across 12 to 20 rivets, with individual clamping forces of 15,000 pounds, creating redundant load paths that prevented single-point failures. Modern welded frames used fewer fasteners and achieved faster erection schedules. But their fatigue life under cyclic loading proved significantly shorter than riveted connections, with weld toe cracks appearing after decades rather than centuries of service. The definitive vindication came in 1955, when a building inspection team investigating structural modifications to a 1915 riveted frame opened connections that had been sealed for 40 years. Harrison, now 73 years old, accompanied the inspection team as they carefully removed steel plates to examine the condition of rivets installed by crews like Miguel Santos decades earlier. The rivet heads remained tight. The steel plates showed intimate contact with minimal corrosion, and no fatigue crack evidence could be detected in connections that had carried millions of load cycles over 4 decades of service. The inspection team leader, a structural engineer named David Walsh, who specialized in building rehabilitation, expressed amazement at the condition of the 40-year-old riveted connections. "Mr. Harrison, these rivets look like they were installed yesterday. The clamping force is still intact, the plates are in perfect contact, and there's no sign of the fatigue damage we routinely find in welded connections half this age. You built something that was designed to last centuries, not decades." Harrison nodded, understanding that Walsh had articulated the fundamental achievement that distinguished American riveted construction from the efficiency-focused alternatives that had followed. The correct mechanism had mattered more than apparent sophistication or theoretical advancement. Hot-driven rivets, properly installed in distributed patterns, had created connections that worked in harmony with steel's natural behavior under load, thermal stress, and time. The triumph belonged not to advanced technology, but to the wisdom embedded in techniques that understood how materials behaved over the long term. As Harrison left the inspection site, he reflected on the decades of vindication that had proven his original insights correct. American ingenuity had succeeded not through revolutionary innovation, but through careful attention to mechanical principles that governed how steel frames carried loads and accommodated movement. The riveted connections he had specified in 1898 continued to perform their structural function with the same reliability they had demonstrated on the day of installation. While welded structures required ongoing maintenance, inspection, and eventual replacement of failed connections, the legacy of Harrison's work extended through every riveted building that continued to stand in cities across America, structures that proved the enduring value of craft over convenience, understanding over efficiency. Because the rivet had performed its fundamental job of distributing load, allowing micro-movement, and maintaining clamping force across decades of service, American builders had created steel frames that demonstrated true structural permanence, proving that lasting strength resided not in rigid welds, but in the accumulated wisdom of hundreds of thousands of hot-driven rivets installed by skilled hands guided by mechanical understanding.